everyone. Welcome to another edition of the FEM at LLNL seminar series. Our speaker today is Rubén Sevilla, a professor of computational engineering at the Zenkovich Institute for Modeling, Data and AI at Swansea University in the UK. Rubén obtained his PhD in applied mathematics from the Technical University of Catalonia in Spain in 2009. His work on NURBS-enhanced FEM led to several awards, including the Best PhD Thesis Award by ECOMAS. He's currently the president of the UK Association for Computational Mechanics and the chief editor of the European Journal of Computational Mechanics. I've known about Rubén's work from his many papers in meshing-related topics and his participation on the organizing committee of the SIME IMR, and I'm really excited about what he has to share today. Rubén, the floor is all yours. Please take it away.
Thank you very much. Let me share my screen. Okay.
See the screen? Yep.
Perfect. Thank you very much, Ketan, for the introduction and actually for the invitation to deliver this talk. It is a real pleasure to be talking to you guys. I'm going to present our work on machine generation and adaptation using green AI, and this is obviously joint work with a team. So these are the team at Swansea University. So Obeid Hassan and Jason Jones, the pro-academics, and Agustin and Callum, two PhD students, and Sergi is an MSc that spent 1 year doing his dissertation with us a couple of years ago. So Swansea, in case you don't know it, so I'm talking to worldwide audience, is second largest city in Wales, which is a country in the UK. And we are based in the Bay campus, which is one of the few campuses that has their own beach. But I can actually disclose that we don't use it very often to swim or anything because it's too cold over there. Okay. But anyway, it's quite a nice place. The Gower Peninsula, which is next to us, is a place of outstanding natural beauty. So if you like nature and hiking and so on, it's a perfect place to be. And the other thing that is really famous, and probably you know about it, Swansea, probably the only know that you know about Swansea, is the only one is that Professor Sikevich came in here and developed his career since the 1960s. And he's one of the recognized fathers of the finite element method. So let me start by basically talking a little bit about the carbon footprint of engineering simulations. There is an increased concern about not just the cloud, but the general use of HPC facilities and its implication in terms of carbon emissions. And there are plenty of news, but I'm going to talk just a few seconds about the last one, the one on the bottom right. This is a study that was made by astronomers, and basically they quantified the carbon footprint associated to the activities, the research activities. And what they came up is with this graph in here that shows that offices, the use of large facilities like observatories is surprisingly low. Flights is on the top in here, and it's increasing criticism sometimes of organizing too many conferences and us traveling to too many places in order to do research. But actually, the reality is that on the top and by far, the most contributor aspect of the research is the use of supercomputers. Okay. So if I bring it back to our research, and our research is focused on the use of computational fluid dynamics for the design of aircraft, let me have a look, for example, here in this graph, what I represented schematically is the flight envelope. Okay. And to cover that, you normally would run, conservative approach, I would say 200 runs to cover all the flight envelope. Okay. Each one of these runs, traditionally, nowadays, it would use the order of 100 million elements, and it would take 12 hours using 500 CPU processors. Okay, that's just a rough estimate. And it's a rough estimate because the 200 runs is really conservative. This is at the very early stages of design. When you look into a geometry, you would go naturally to 1,000 simulations. And this is if we're talking about civilian aircraft. When you go to military aircraft, this number could go easily to 10,000 simulations. Okay. So if we quantify as being conservative, 200 runs with this number of elements using this computing architecture, that equates to 1.7 tons of carbon emissions to perform these simulations, which if you want to put it in a different figure, that's equivalent to 15 megawatt per hour or almost 10,000 kilometers in a passenger car. Okay? And if the situation is not bad enough by looking at these numbers, when you go and read the CFD, the famous CFD vision report by NASA, basically one of the statements that they have in there is that in 2030, we expect simulations with 20 billion elements to be commonplace. So if you go and you do these numbers again, to perform the 200 runs, we're going to be talking easily about 150 tons of carbon emission, which is equivalent to going 20 times around the world. It is in a passenger car. So that gives you really an idea of the cost of the simulations. And one of the reasons for these high cost and high implications, environmental implications of using HPC, is basically the way that things are done in many industries, aerospace industries in particular, because they need to perform parametric analysis. So they need, for a given geometry, to run many cases, varying the angle of attack, varying the Mach number. They don't want to do meshes for each one of the cases, and they end up doing what they call the grid mesh approach, the fixed mesh approach, in which basically they mesh with almost uniform spacing around the aerodynamic object. And the only reason they do that is because they will run all the simulations with the same mesh, and they don't need any human intervention, which for them is the most time-consuming part, having a human defining the spacing for each one of the simulations. And because ideally, what you would like is that for different configurations, different Mach numbers and angle of attack, for example, you would use meshes that are tailored for that simulation, that really would use an efficient use of your computational resources. But at the moment, they are not doing it because they need intensive human intervention at this stage, and this is the most expensive part for them, the time of a human. So basically, the idea of our research is to, and this is the outline of the talk, is to try to predict with neural networks what would be the near optimal spacing. We are not going to be too ambitious and call it optimal. I don't think we can call it optimal, but we can call it near optimal. It's going to be a very good mesh to start with for a new simulation, only refining ideally what is needed. So let me start with this part, then I will present on the second part, how do we extend all of that for transient problems. I'm thinking on higher order methods and degree adaptation using neural networks. This will be the two main blocks. So let's go for the first one. This is the typical design cycle. You have some operating conditions and a given geometry, and you spend time, if you want to do things efficiently, you spend a lot of time defining your spacing function. This is what I was mentioning before. After you've done that, you generate your mesh, you perform your simulation, and you assess the accuracy of your solution. If it is a suitable accuracy, you finish. And if not, you need to go redefine your spacing function and generate the mesh again. Now, our idea is simply to insert in the middle here a neural network that learns from existing data and is able to predict the spacing function in such a way that is no longer a bottleneck in terms of time and human hours invested in this process. Hopefully, what we are aiming to achieve with that also is to reduce the number of iterations in this cycle. So basically, we aim to produce a mesh that is good enough to obtain the accuracy that you need. So we are aiming to increase the speed of automation, accelerate mesh-independent studies, overall with the aim of speeding up a design process. And we're also thinking on reducing the carbon footprint of current simulations in the industry. And finally, the last point, as you probably may know, mesh generation and preparation of models for simulation is normally said to be the bottleneck in the whole simulation pipeline. But despite that, there are a lot of more investment and a lot of more people working in the development of solvers, new methodologies for solving partial differential equations. And it's very few people dedicated to the mesh generation aspects and geometric defeaturing and cleaning and so on and so forth. So basically what we are aiming to do here also is to embed into this artificial intelligence system some of the previous knowledge of people that have been experts that have been generating meshes for particular simulations. All this data at the moment is really not used. So the first thing that I would like to cover here is if we are aiming to predict the spacing, how is the spacing normally defined? And there are two ways, traditionally. They are not disjoint, so they could be used or both together. The first one is we could use a background mesh, which basically is a way to define a discrete nodal spacing function. So basically what we do is we create a very close mesh. This mesh is completely automatic. It's not refined everywhere. It could be uniform, could be structured, could be anything. And then we define a function at each that gives you a nodal value at each node of this close background mesh. This basically defines using linear interpolation discrete spacing, and then you can use it in your mesh generator algorithm in order to query for what is the spacing needed at any particular place, and this will give you a mesh like that, where in blue you see the lower or the low values of spacing, and that gives you smaller elements when you generate the mesh. An alternative is to use what we call sources. So basically a point source, and this can be extended to lines and planes, but I'm going to just restrict myself to point sources for the sake of simplicity. A point source is basically the position in the space, decide the spacing at that position, and radius of influence. So the expression is something like that, but I think it's better explained with a picture. So you define a point, okay, which is the coordinate I see here in this formula. You define a radius, which is the first radius in yellow, would be this R1, and a second radius, which is R2 in black. And basically what you are doing with this expression here is saying that the spacing will be constant within the first radius. It will double as you travel radially from the first to the second radius, and then it will increase exponentially. So if you define this source as represented here, the mesh generator will create a mesh like that. And obviously you can put several sources, and when they interact, the only thing you have to do is take the minimum of all the spacings. So this is all very good, but the problem is that handling mesh sources in particular, or a background mesh in 3 dimensions, and specifying what is the spacing at every location is time consuming. And this is where, at the moment, there is a lot of investment of human hours. Imagine this case in here with the mesh sources. You need an expert engineer that is taking decisions of where to place the sources, what spacing to use, what radius of influence to be used, etc., etc. And this is why at the moment companies are heavily relying on expensive simulations with a fixed grid that is capturing all the features, okay, with a necessary computational cost. So I'm gonna present 2 systems, 2 neural networks that we've designed. The first one is to predict the spacing on a background mesh, and the second one will be to predict the sources. Okay? So I'll take the first one. Basically, we start with data. These companies that we're working with, they have a lot of data from previous projects, so we do plenty of solutions that we can learn from. So if you give me a solution like the one shown here on the top left, which is a pressure field, floor and the wing, the first thing we do is we translate this pressure field into a spacing function. And the way to do that is to use basic concepts of error analysis. Okay? So basically, we take the spacing at a node. Is going to be related to the Hessian, given this expression in here. So you need to compute the Hessian of a key variable. We use pressure for implicit flow simulations. And once you've computed the Hessian matrix, which needs, you need to reconstruct first derivative and then the second derivative in a traditional way. Once you've computed this Hessian, you can compute the eigenvalues, and this will give you a function of the spacing, which is what is plotted in here. You can see that blue, which is small spacing, is associated with areas of higher gradients, like the leading edge. Now, without going through all these expressions, basically what you have in here is eigenvalues of the Hessian matrix. You got a cap on minimum and maximum spacing, and this is to avoid the degenerate cases, because you might have places where the flow is absolutely constant, it's free stream flow. And basically what this formula, if you don't cap it, basically is going to give you that you need to use an infinite spacing in that area. And similarly, when you have shocks, you can have extreme small values of the spacing that is going to lead to bad quality elements. So you put this limit in here for those reasons. And we also use a scaling. This is traditional in mesh adaptivity. We use a scaling that basically controls where the minimum spacing is going to be associated to. Is it going to be associated only to one point, the point with the maximum variation of the solution or to a range of points. And just to illustrate it, if you associate no scaling, if you put this s equals to 1, only the minimum spacing is going to be associated in this case to the trailing edge because you've got the singularity there. Okay? But that will mean that you're going to miss features like shocks. So if you reduce the scaling, what you are going to allow is that the minimum spacing is distributed to more nodes, more elements in your mesh. Okay. So that's how you translate a given solution into a spacing. We'll repeat the process for all the training cases that we have available, all the different pressure fields that you can see here. It could be for different flow conditions. It could be for different geometries. Okay, we've done both, and I will share examples on both. After translating this to a spacing function, if we want to use a traditional feed-forward neural network, we need the output layer to have a constant number of neurons. So in this case, this is not still there yet because these simulations, they could have been done in different meshes. Okay, so what we do is we define a background mesh, which is a closed mesh with no specific refinement anywhere, and we are going to interpolate the spacing function for each case into the common background mesh. Okay. And the interpolation we do is basically what we call it a conservative interpolation. Basically, you take a point on the background mesh, you take the patch of elements surrounding this node, and then you project this patch into one of the simulation meshes, one of the computational meshes you have. And you take the minimum spacing of all the nodes inside this patch, and you associate it to the node of the background mesh. This basically allows you to represent the spacing in this common mesh. Okay, that's interpolated the spacing for each one of the cases. One of the things that is worth noticing here is that you see how the spacing is actually smooth. So for example, all this area of the smooth spacing in here, which is necessary to capture the shock, is actually expanded a little bit. And this actually is acting as a safety factor. This allows you to make sure that when you do the predictions, you are not going to miss any feature. Okay. And at the same time, we're using a background mesh, which is closed. This is going to reduce the number of outputs required in the neural network. So it's going to speed up the training. So the architecture is really simple. It's a feed-forward neural network. The input layer is basically the flow conditions, so rectangle and angle of attack, and geometric parameters. And the outputs are the spacing at each one of the nodes of your background mesh. Needless to say that if you are considering different geometries, you will need a mesh morphing algorithm in order to morph the background mesh into each one of the configurations. Yeah. This, I believe, is quite standard. The second approach is using mesh sources, as I mentioned. So the algorithm goes in the following way, or the strategy goes in the following way. From a given solution, again, we started at the same situation. We compute the spacing function as done before. But now we have devised also an algorithm that allows you, from a given spacing function, to compute what are the set of sources that when you generate a mesh with this set of sources, it will give you the spacing function that is able to capture this mesh. Okay? This is basically an algorithmic strategy. It's described in this paper. I'm not going to go through that because it's got a lot of steps. But basically, it's marching through the mesh from the places with minimum spacing, placing sources in there that capture this spacing, and moving away in order to add sources as required to capture the spacing function that will capture that solution. Okay. Now, we repeat this process for all the simulations. And what happens, not surprisingly, is that each one of the cases will lead to a set of sources with a different number. So the first solution here, with 217 sources, you will capture the spacing required, but a different case might have two shocks, one on the top, one on the bottom, and it's requiring more sources. So how do we make this consistent in order to use, again, a fixed number of neurons in the output layer? Is basically we devise an algorithm that takes the first set of sources, then it visits the next case, and it queries which of these sources, when you add them, will alter the spacing of the first case. And if this is the case, that means that you need to add that information. So basically you sweep and you obtain a fixed number of sources, which is in this case 1,660, First, you sweep down in order to query what new sources need to be added, and then you sweep up and start adding these sources to make all the cases consistent. Now, once you have it, again, the architecture is fairly simple. Input layer is the same, flow conditions and geometric configurations, and the output now is going to be the characteristics of each one of the sources. So here, notice that per source, you have 3 coordinates in 3D, you have 1 spacing and 1 radius of influence. So it's 5 outputs multiplied by the number of sources. Okay. Now, how does this work? Once you've trained the neural network, basically it gives me unseen cases, could be flow conditions or geometry. I use my trained neural network to give you the set of sources. You could directly use this set of sources in the mesh generator, but actually we know by construction that there will be many sources that will be redundant. So if I take you back to this case in here, you could see that all these cases, they had few hundreds only of sources required per case, but in order to make it consistent, I took it up to 1,600. So basically one thing we do, and this is only done to speed up the mesh generator, is we remove the redundant sources. So we remove any source that can be removed without altering the spacing, because it's actually redundant. And after that, you're ready to generate your mesh and perform your simulation without having to manually insert all these sources. So let me show you an example. Excuse me. And I'm going to take this 3-dimensional on a wing with variable flow conditions. Okay. So this is going to be parameterized with a Mach number that going from 0.3 to 0.9. So it's covering subsonic and transonic regime. The angle of attack from 0 to 12. Implicit solution for the moment, implicit compressibles of the Euler equations. And we're going to increase the number of training cases from 10 to 160 and use 100 test cases unseen by the network in order to test the accuracy. We have no idea of what number of hidden layers of neurons to use, so we are going to do a brute force grid search. So we are going to run for hidden layer from 1 to 6 and neurons from 25 to 250. And I'm going to show you results for the 2 neural network architectures. So one is the one that uses sources. In this case, we are talking about of the order of 20,000 point sources. And remember, you need to multiply this by 5 to know what is the number of outputs of your neural network, because each one of the sources has 3 coordinates, a spacing and a radius. Okay, so we're talking about a neural network with 100,000 outputs in here. With the background mesh, the size is substantially reduced, so this is promising because we use a mesh with only 14,000 nodes, and you only need to predict 1 scalar per node of the mesh, which is just the spacing and the background mesh. This is a bit of the tuning, which sometimes I miss people showing these graphs. They only show you the good predictions they can make, but not the nitty-gritty behind it. So this is what we did in terms of hyperparameter tuning. So we vary the number of neurons in the x-axis and the number of layers, hidden layers on the y-axis. And what you see in these 5 graphs are the R-square for the 3 coordinates on the top for sources, the spacing, bottom left, and the radius of influence, bottom right. And what you can see, the first thing you could see here is that the spacing is very easy, the position is very easy to predict. So you got really high R-square values, nearly 100. The spacing is a bit harder, and the radius of influence is even harder, okay? Important also to see that we don't need really deep networks, okay? We went to 6 layers because we wanted to explore really the hyperparameter space, but with shallow networks, with 1 or 2 layers, we are getting good accurate predictions, good enough accurate predictions, I would say. And on the right is a study of how the accuracy, the R-squaring here is increasing as you increase the number of training cases. Okay? You can see the 3 coordinates on the top, really accurate results even with 10 training cases. But for the radius of influence and the spacing, you need a few more in order to achieve good values. Now, let's have a look at the performance in more visually, and then we'll try to quantify also the performance of each one of these flow approaches. So this is for the case with variable flow conditions, and I'm going to pick up one of the unseen cases by the network. And it's a relatively complex case because you've got an undershock in here. So this is these are the flow conditions. This is the target mesh on the top left, and the machine learning prediction on the bottom. So visually, it looks like the machine learning is actually predicting where to refine pretty good, I would say, in a pretty good way. But then if we try to quantify, basically what we are going to do is we are going to go to every point in your mesh, and we are going to measure the ratio between the predicted spacing and the target spacing. And this is the histogram that you have on the bottom right. You got two bars, one corresponds to two colors, one corresponding to the approach with sources and one with the background mesh. And in terms of quantifiable accuracy here, you can see with the sources, 72% of the points predicted within 5% of the target. And with background mesh, this goes up to 94%, okay, which is pretty good. And we are using quite a lot of training cases, I would say, 160 training cases for this. Now, several comments in here. Number one, 5% of the target, when we're talking about mesh generation, is really unnecessary, okay? When you think that a mesh generator, when you ask for a given spacing, imagine that you ask for a spacing of 1. It will give you a spacing of 1.2, 1.3 easily, because sometimes you have no other way of closing the spacing, or it will give you a spacing of 0.9, 0.8, 0.7. What is the threshold that normally you need to consider as acceptable when you ask for a mesh? Well, if you're asking for a spacing of 1, excuse me, you need to accept up to square root of 2 normally. This is the magic number that mesh generators use. And the reason is that if you go above the square root of 2, then basically you would split the element and you will get something with a smaller spacing, but at a closer ratio to the spacing you wanted. Okay? The square root of 2 reason is because if you split an element with a square root of 2 size and you are asking for 1, the spacing you will get is square root divided by 2. Okay? So it's basically in the middle, the 1. Excuse me again. So this is one comment. What I'm trying to say is that we are being a bit unfair with ourselves by looking at these histograms in here with 5% being our tolerance, let's say. Okay? Normally, if you look at as I was saying, at the square root of 2, which is a value that a mesh generator will fluctuate when you require a given spacing, with only 40 training cases, we are almost hitting the 100. Okay? So that gives you an idea of really the accuracy of the predictions. Now, another thing we did is to actually use the meshes that are predicted by the neural network in order to perform a simulation and see how accurate are the results. And what you can see here is for different flow conditions, the pressure coefficient for the target simulation. So it's basically the simulation done with the target mesh, the ideal mesh, and the simulation done with our predicted mesh. You cannot see any difference visually. And then when you quantify that with the aerodynamic quantities of interest, so lift and drag, basically we see that we are within the accuracy that is expected. Right. More complicated examples include geometry. Okay, we've been talking so far about flow conditions, only 2 parameters. When you start considering variable geometry, then the number of parameters really goes high. So here I'm going to consider this full aircraft configuration. Excuse me. With 11 geometric parameters. This figure basically gives you an idea of what is the variation that is induced by these geometric parameters. And I'm going to consider transonic flow conditions. Okay? So all the solutions are going to exhibit shocks, actually. Okay. You got, in this case, with 11 parameters, I'm going to show you results with using very few number of training cases for such a high dimensional problem. And you can see here solutions. You can see different nature of the shocks. For example, in the top one, you got the shock running across the whole wing. This is well predicted by the neural network. On the bottom, you got a case that is even more complex because the shock starts to interact with the engine intake. You need this refinement in this area to capture this interaction, and this is actually well predicted again with the neural network. And the histograms, as I say, using this scaling in the bottom, we can see that obviously with 10 and 20 training cases, you are not going to reach 100% of the points predicted perfectly. But it is quite impressive to see that with only 20 training cases, you can hit 90% of the points in the mesh predicted with the accuracy that is acceptable. Now, let me talk in one slide about part of the title, which is the green AI part of the title of the talk. So basically, our objective was to increase efficiency compared to what the current industrial practice is. And practice in industry, as I mentioned before, is to use a fixed mesh and run all the simulations on the same mesh to avoid having a human deciding where to refine for each case. So if you go for this approach, then in terms of mesh generation, you spend nothing. You spend 1 hour because you generate this mesh. This one I think it had of the order of 40 million elements, but you're going to do that once, so that takes you nothing. But the problem is that the CFD simulations that you're going to perform quite a few, they are going to become very expensive. And this is the time spent, more than 3,000 hours. And these are the carbon emissions, half a ton carbon emissions to perform this parametric study in this geometry. Now, if we do the quantification for our approach, then what you're going to observe is first, in mesh generation, you're going to spend more time. Obvious, because for each one of the simulations, for each one of the flow conditions, you're going to need to generate a new mesh. So this goes up to 24 hours for mesh generator. But then the big advantage is that your simulations will become way cheaper, okay? Because you got a mesh that is tailored for that geometry, we are reducing the time substantially and the carbon emissions substantially. Now the question is, can we call this green AI? It's certainly AI because we are using neural networks. And the answer is no. The definition of green AI is that you are going to improve or you want to reduce the amount of computational resources and carbon emissions caused by the use of HPC if you account for training and tuning. Okay, and this is something that is very often is hidden. I don't think we should be hiding this information. We should be including in this table. So basically here I'm including all the time that we spend training, but also tuning. And tuning means running for different number of neurons, different number of layers, and even quickly repeating the training as we do in order to remove the influence of the initialization of the weights of a neural network. Okay, all of that is included here. I'm not surprised because what happens now is that the time of tuning and training becomes dominant. Okay? And I think this is why in many occasions this time is hidden, because if you are not careful, this will become the dominant cost of your process. The good news is that the resources that you need for training our neural networks are relatively small. Okay? So the carbon emissions associated to this tuning and training is very low. And by reducing substantially the CFD hours, which use parallel processing and so on, you are reducing substantially the carbon footprint. And the overall conclusion is that we can reduce the carbon emissions compared to current industrial practice by a factor of 35, which is quite impressive in my opinion. Now, the next thing we've done is to try to extend this to isotropic spacing. So far, I've been showing you all isotropic spacing. We wanted to extend it to anisotropic. To capture what? To capture directionality in a more efficient manner. Because when you look at these solutions, there are clearly directions along the shock, for example, where the pressure is really not changing in this direction, but it's changing in the transversal direction massively. So the optimal use of your discretization will be to stretch the elements across the shock in order to minimize the number of elements whilst capturing the high gradients. So the idea is basically to extend our approach to predict a metric tensor, because this is how you describe anisotropic spacing. You need 3 orthogonal directions, and you need 3 spacing in each one of these directions. So the strategy that we followed, because you could say, okay, if you need to predict 3 directions, these are 3 vectors with 3 components, so 3 by 3 is 9 in total, plus 3 spacing, that's a total of 12 outputs that you need to predict per point. But it's actually not true. You can do a bit better. And what we do is we look at the first direction, and the first direction is the one of minimum spacing. And we express it in a spherical coordinate, which means that we need only 2 angles to represent that direction. And then we use orthogonality. We know that the second direction is going to be an orthogonal plane to the vector E1, to the first direction. So it's going to be somewhere in the plane, for example, here. And again, we don't need the components of the vector. We can use polar coordinates on this perpendicular plane. And the third direction, you don't need to predict it at all, because if it has to be orthogonal to these 2 vectors, it's already given. So effectively, you only need to predict 3 angles and 3 spacings in order to enhance our system to predict anisotropy. So we have the first example in here. Is again on an M6 wing with variable flow conditions, so Mach number and angle of attack, and using 80 training cases. Now, for obvious reasons, you are trying to predict more information, so 6 outputs per point rather than just 1 for isotropic spacing. So you're going to need more cases. And you have 2 unseen cases, the solution on the left, on the center is the target mesh, and on the right is the prediction, which visually makes a good job. And if you zoom, you can see it's really stretched, okay? So you are producing an anisotropic spacing in here. A similar graph to show quantify the accuracy. With 80 training cases, we are almost predicting all the nodes perfectly. This is the first spacing, is the spacing of minimum. Sorry, is the spacing in the direction where it is minimum, so referred to the shock. And then second and third spacing, all of them well above 90 and almost reaching 100%. For a more complicated case, again, going back to the full aircraft configuration with 11 geometric parameters and only using 40 training cases. Okay, so I'm showing results with the minimum number of training cases possible, what accuracy you can achieve. As here you can see again that we're well above 90 for the most important spacing. We consider the first one the most important because it's going to be linked to how accurate you can capture the shock, and also doing reasonably well in the other directions. Now, all of that, I'm going to move on because all of that is done for implicit flows. So we've played a little bit with viscous and turbulent flows, but we've done it in 2 dimensions. This is the work basically of an MSc student that spent 1 year with us. And we found a few challenges, okay? I'm not going to lie. And I'm going to present them here, and I'm going to present the solutions we found to them. But all the challenges are really induced by the use of highly stretched elements in the computations with related to turbulent and viscous flows, okay? So boundary layers, shear layers, and so on. And all the challenges come from the fact that we need to compute the Hessian in order to compute the spacing function that we're going to try to predict, which means we need to reconstruct gradients. And when you look at the computation of a gradient, it could be done in different ways. You can use a finite element approach, a finite volume, but no matter what you do, you're going to end up dividing by an area of an element in 2 dimensions. And at these areas, on the boundary layer or on the shear layers, you're going to be handling elements with an area of the order of 10 to the minus 9. So any minor issue, any minor inaccuracy in your solution is going to give you trouble. Okay. So take up one case, the typical case in the NASA website, RA2822, transonic turbulent flow. And you look at the pressure distribution. Overall, from a certain distance, everything looks okay. So no major issues in here. But then if you start zooming, and you need to zoom a lot, so this is a zoom near, it's on the lower surface, very close to the leading edge. And when I say that you need to zoom a lot, is we're talking about 10 to the minus 3 is the scale that you see in this figure, and the chord length of the wing is 1. Okay? What we saw with our code, with our simulations, is this small oscillations in the last layer of elements. This are the contours of the pressure. Initially, we thought even that it could be something with our code, something wrong with our code. We downloaded the solution from the NASA website, and we saw even bigger oscillations. Okay. So basically, this is telling me that this is not fully converge the solution within the boundary layer. You cannot fully converge it. Okay? And you got tiny, tiny, tiny oscillations, which they don't have an effect on the width and the drag. You don't see anything in there. You got good answers, good comparison with experimental values. Okay? And this is what everybody's reporting. These oscillations are here really, really tiny. I insist, even the scale. But the problem is that these oscillations, which are so tiny, when you use a reconstruction procedure and at the boundary layer, you are dividing by a factor of 10 to the minus 9, all of that explodes. And basically what is going to happen is that the spacing is going to be dictated by this small physical oscillation in here. Okay? So basically what we proposed, basically let me show you first what would happen if you don't do anything, if you just take the spacing as given by this solution. Then basically the spacing function that you're going to get is something like that. All the refinement in the boundary layer, nothing capturing the shocks. And this is because your gradient reconstruction is basically biasing everything towards the boundary layer. So what we've done is a simple smoothing. So we use the fact that we have a structure mesh in the boundary layer region. So we take the nodes that follow a normal direction and we do a smoothing. So basically we do a fitting with a cubic spline in here. Okay. And with that, we can remove this very local effect, and all of a sudden, you will have spacing that really reflects the variation of your solution. Okay. So you are removing this high influence near the boundary layer. The other thing you need to be a bit careful is to use not one key variable. We've been using pressure only for implicit simulations, but if you use pressure only for viscous ones, you're going to miss features, especially on the wakes. Okay. So we consider either pressure and density or pressure and Mach. We ended up using pressure and Mach because you got a better capture of the wake. But basically, you need to combine more than one key variable, okay, in order to do your computation of the spacing. And the last thing we wanted to do, and we played a little bit with this student, is basically to link the geometry to the cut. So basically, I'm going to show you one example only in this 2D, which I'm going to predict what is the spacing required for different geometric configurations, but the geometry is parameterized with the NURBS control points. So you can see the control points of the cut, and they are allowed to move within each one of these rectangles. And you can see the high variability in the solution that in the geometry that you get. And so predicting the mesh for each case is going to be challenging because the solution is going to be quite different for each geometry. This is the example that showing you for transonic turbulent flow conditions, 23 geometric parameters, so it's really high dimensional problem. Excuse me. Target mesh is on the center and predicted mesh is on the right, but as usual, it's better to quantify it with the histograms. Obviously, for obvious reasons, we need a high number of cases because the dimensionality of the problem is really gone high in here, 23. So if you really want to hit higher percentages to 90%, we're talking of 640 training cases. And when you think about it, 640 training cases for a problem in 23 dimensions is not that high when you put it in perspective. And also we assess the accuracy in terms of how good is this mesh to perform a simulation. So we use the predicted meshes to perform simulations, and we compare lift and drag, and we observed again a very good accuracy. So the meshes are really suitable to perform simulations. So you are trying to bypass the need to do repeated remeshing. Right, this takes me to the last part, which is everything I showed so far is steady problems. And we're also interested in solving transient problems for obvious reasons. But in this case, we are aiming to use higher order methods. I think that this is pretty well established nowadays, that for transient problems, higher order methods are really beneficial because of the low dispersion and low dissipation errors associated to these methods. Now, there are plenty of methods available, higher order methods. Our preferred method is hybridizable discontinuous Galerkin. And one of the reasons we like this method, I'll show you in a second, is because you take the momentum equation, and as in many other DC methods, you split it into two first-order equations, introducing what is called a mixed variable, L, which is the gradient of the solution, the symmetric gradient or a scale symmetric gradient, if you like. Now, these two variables, the velocity and its gradient, will become independent variables, okay? Which in principle, you may think that you are increasing the computational cost. But then in HGG, actually you solve the problem in two stages. You write in each element a local problem, which contains the momentum equation, the equation for the mixed variable, divergence-free condition. We're talking about incompressible flows now. And we introduce also what is called the hybrid velocity. So I'm increasing the number of unknowns massively here. So my initial unknowns were velocity and pressure. I'm using a mixed formulation, so I'm adding the gradient as an extra variable, an extra unknown. And I'm also adding now what we call the hybrid velocity, which is the velocity at the faces of the elements. And all of them are independent variables that you need to solve for. And then this is in each element. And on top of that, you need a way of communicating in between elements. So basically, the fact that you allow this continuous solution, you need what we call the transmission condition. So you impose the continuity of the velocity and the continuity of the fluxes in the normal direction within internal phases. So this might look like a very complicated problem. The trick in here is that we're going to solve the problem in two stages, as I mentioned. First, the global problem. And the global problem only involves velocity on the faces of the element. So on the interface in between elements in writing here, you've got degrees of freedom for velocity, and only one value of pressure per element is the mean value of the pressure at the center of the element. This is what leads to the global coupled system of equations. This is the costly part of the HCG. But after you've done that, then you go element by element, and you can compute the velocity for whatever order you decided to use, the pressure for whatever order you decided to use, and the velocity gradient. And I insist that this is an element by element problem, which means that the solution in one element is completely independent on the other. So all of that can be done in parallel in a trivial manner. And the reason why we like HCG is because it allows you, the fact that you have the velocity and its gradient as independent variables, and they converge optimally, both of them, with the same rate, k plus 1, k is the order. It allows you to build what we call a superconvergent velocity. So here you got for this coordinate flow, a typical test case with an analytical solution, you have convergent rates for different degrees. Each one of the colors is a different degree. On the x-axis is the spacing, on the y-axis is the orthonormality error. And obviously, as you refine the mesh, the errors decrease, but very important, the error decreases with the same rate for velocity and its gradient, and this allows you to build what we call superconvergent velocity, this U star, that converges faster. In particular, converges at a rate of k plus 2. And the idea here is that if you got two approximations of the velocity, and one is converging faster than the other, you can build a very cheap error indicator. And you can use this error indicator to perform degree adaptivity. And that's our strategy for solving transient problems. Now, an illustration of how the degree adaptivity works for a steady problem before I take you to the actual transient problem of interest is the one flow. This is the velocity magnitude with a high radius near the boundary on the bottom. And this is the degree map that you end up with higher degrees near the boundary and lower on the top part. And just to convince you that this error indicator is reliable, is sufficient, you can compare, because the one flow has exact solution, you can compare the exact error on the left to the error indicator. And it does a very good job. And remember that all of that is cheap, because you only need to solve element by element problems in order to build the superconvergent solution. Okay? So the dominant cost is really the solution of the global problem, not the post-process to obtain the superconvergent velocity and the error indicator. So I'm going to apply this now for a transient problem. I'm going to apply this idea. So I'm going to put a perturbation of the velocity. This is a rectangular domain. Free space over free stream, this is air, and I'm going to put in here a perturbation of the velocity that is going to travel from left to right in the free stream, following the free stream velocity. On the bottom left, you have the degree adaptivity. Top center, you got the reference solution. This is with a high order everywhere. And on the bottom right, you can see, corresponding to the activity on the bottom left, what is the degree. And if you run it, and you look at what happens here, basically, we lose the accuracy on the degree adaptive solution. And in short, what is happening is the following. You take a snapshot of the solution, you compute the superconvergent velocity, you estimate the error, and you adapt the degree. But then basically this solution is going to travel from one position to another, this perturbation of the velocity. So basically, we could have a perturbation that is traveling to a place of the mesh that is not suitable to capture that perturbation. The mesh is not refined, the degree is not high enough. And you can see it on the right. I mean, you have high degree in this area, but at the next time step, the solution is going to travel to the right to a place where you are using P1, and you're going to dissipate that. It's worth noting here that this happens because we are interested in high order. And the interest in high order is not just in space. We are also using high order implicit Runge-Kutta time integrators, which means that we are advancing the solution at high CFLs. Okay, our method is unconditionally stable, so it's only a matter of capturing the physics properly. There is no restriction on the time step. So we're using high CFLs, and the solution is traveling to a place that is not refined. Now, what is a stupid solution to that? And something that some people do is, well, you advance the solution in time, you perform the adaptivity, and then you go back in time and advance the solution again. So you repeat the time step, and in that way, you will make sure that the areas where the solution is going to travel have already been subjected to degree adaptivity. You have increased the degree, so the elements will be able to support with accuracy the solution when it reaches. And this is what you see in this simulation. Reference in the center, on the left, normal adaptivity, losing the solution, on the right, repeating each time step, and you can guarantee accuracy. But as you can obviously think, this is not efficient. You are doubling the cost of each simulation. So what we do, our idea here is to train a neural network to predict the solution at time n+1. Okay? So we are going to collect data from simulations, and basically we are interested in solving this problem that I'm showing you. Let me go back. Solving this problem with perturbations of the velocity that are parametric. So we got change in width of this perturbation, change in intensity. We could even be changing the angle. Okay? And in that scenario, what we're going to do is we're going to run a few simulations and collect data, and we're going to train a neural network that takes, at a given point in the mesh, takes surrounding points, top and bottom, left and right, in the spirit of what it would be, for example, a stencil, you find out differences. And we are going to take the information at those points at time n as input of a neural network and predict the velocity at the next time step. Okay. All of that, we are going to do it from data available from simulations, as I said. These points are not mesh nodes. This is important because we're using unstructured meshes. So the points of this sort of extension, they are overimposed into your unstructured mesh. And to capture the data, basically, you interpolate your velocity and break shuffle the unstructured mesh into these supporting points. And just a technical aspect that I think is important is you might notice that in our simulations, then you could have a lot of places where nothing is happening. So basically, the solution is constant. So basically, to remove the bias associated to that, we remove the redundant information, okay? To avoid the neural network to be biased towards places where basically the input and output is the same. It's a constant field. And let me show you, to finalize the last simulation, is reference on the left, degree adaptivity on the bottom left, which is losing us the amplitude, as I mentioned before. And on the right here, you got the degree adaptivity, but without a prediction. Okay? You can see how the degree adaptivity preserves with the prediction the solution of the reference configuration. But more important, if you want to quantify that, you got a plot here on the right that shows time and relative error, maximum error compared to the reference solution. And it clearly quantifies the benefit of using this neural network. Your errors are kept below 5% or even less. Whereas if you don't use this prediction, the error really grows very fastly and goes beyond 50%. So I'm going to close with that. I presented two AI systems to predict spacing, one in the context of steady problems. It predicts isotropic and anisotropic spacing. And the meshes have been proved to be suitable to perform simulations. And this process has been proved to reduce computational cost and carbon emissions compared to current industrial practice. The second part of the talk, I presented this AI system to predict degree adaptivity, to aid a degree adaptivity process for transient flows and avoids the need to repeat time steps in order to guarantee accurate simulations. So thank you very much. Thanks for listening. And if you want to ask any questions, please go ahead.
Hey, thanks, Rubén. Some virtual applause. Are you? Right. Yeah. So, do folks have questions? You can maybe raise your hand. For one of your earlier slides, Rubén, where you were showing the hyperparameter study.
Yep.
Can you go back to that? I noticed that it was interesting. It seemed like
this one.
Yes, for the top right case where you have the maximum number of neurons and number of layers, the performance drops down for these bottom two plots.
Yes.
Why?
For these two plots, this is the spacing.
Right.
This is the radius of influence.
Right.
I think, to be honest, my feeling is here is that at some point, this is seen in other problems, at some point adding so much nonlinearity to a problem that doesn't really have this nonlinearity is actually not helping at all. And this is what we see here, which is, it's not just the dropping. Here is the fact that you can add layers and more layers, but you never improve in what you would get with two layers, really. So going really deep in number of layers is not really helping massively. Okay?
Yeah, that's very interesting.
Which for us is really good, because that means that our training times are really low. Yeah.
Yeah, and I like that you try to keep, the number of inputs to a minimum. We also found in one of our projects where, that it helps, it makes a big difference. Just adding a lot of inputs, can increase the strain on these neural networks and significantly impact the performance. And for your background mesh, how did you kind of pick the size for the number of nodes? Was it just like a heuristic or trial and error?
Well, we actually we didn't try many, to be honest. The one we generated is the one we went for. We don't use anything specific because the whole point is that this mesh doesn't need to be refined in any particular way. Right. So the only thing we did, if I may show it, the type of background mesh that we use. This is a section. So this is actually a 3D problem. I'm showing you the section on the symmetry plane for the on and a wing. This is the type of mesh we used, and as you can see, the only thing we did is to automatically do a refinement based on curvature, nothing else.
Right.
Okay, and then the mesh is automatically graded outside. So it's nothing particular. We're thinking of doing something else to really define your mesh automatically, but at the moment there is nothing special.
I see. Yeah, well, I guess that speaks to the robustness of the approach, perhaps.
Well, the thing with the background mesh, I mean, we've done some studies, especially with this semester student. We played a little bit on the effect of the background mesh by manually doing different levels of mesh refinement on the background mesh and how this is affecting your neural network. And what is important is the following. You can see the spacing function in your computational mesh here and the spacing function interpolated on the background mesh. Mm-hmm. So if you go for something that is really fine, for a background mesh that is really fine, then the spacing function will better resemble what it was in the original simulation. So you might think that you are more efficient because you would use smaller elements only in very specific regions. So you might think this is going to be way better to use a finer background mesh.
Right.
Now, the problem is that the finer the background mesh is, the more output you need to predict in your neural network. And that means that you need more data.
Right.
Okay. And also, you are more exposed because you are refining in a very, very localized areas. You are more exposed to potential errors of the neural network. So uncertainty is inherited into the neural network. So you know that you're going to have error in your predictions. What we feel is that using a closed one is actually better because it's safer, because these areas of small spacing are sort of smoothed out. Mm-hmm. And that means that your meshes that you will generate will potentially capture always all the features that you need to, at the expense of producing meshes with some extra elements. But it's always good to be on the safe side, we think, and avoid having to do let's say an adaptivity after generating the meshes. What we've seen is that with this strategy, we predict meshes that gives you the aerodynamic quantities of interest within the tolerance of the space industry. And I think it's partially because of the background meshes we are using, we are being conservative.
Right. Yeah, the results are remarkable. I mean, yeah, it looks counterintuitive. I was also wondering maybe the background mesh needs to be finer, but of course, when you go through the process, you find out that this works out better.
Yeah. And when you evaluate the accuracy for a given number of trainings, you clearly see it. So we did an experiment where we have accuracy for a given background mesh, mm-hmm. and another background mesh with half the spacing. And the accuracy actually decreased on the final background mesh because we were fixing the number of training cases.
Oh. Right. So you need more data then to counter that.
Exactly.
Right. Okay, I see Walt has a question, or go ahead.
Yes. I really think this is some great work. Thank you for this talk. Could you go to your second to last slide, please? Where you have
the slide.
Yeah, you have the gusts moving through.
Yep.
And so I'm wondering about the neural net that's predicting the N+1. Is it trained on this particular solution?
On different cases. So as I mentioned, the objective is the gust, you need to parameterize it. Uh-huh. So you parameterize it and you consider intensity, width, and angle of the gust. Okay. Then you sample this space. So you decide how many cases you want to run accurately to gather data, and you gather this data for these simulations, and then you use that for unseen cases.
Okay, so the gust itself then is a relatively low dimension, but it's run through then a whole simulation and then trained on that.
Yes. Okay. You need to be all of that. I think it makes sense already, at least makes sense to me. Only if you are interested in parametric analysis. So
yes,
when you run the gas and you have to vary different quantities, as I said, intensity, width, and so on and so forth, is when I believe that it makes sense to go and gather some data from some cases and try to exploit this data to avoid the extra cost in new simulations.
Yeah. No. This is very helpful. This is exactly the sort of, we're trying to parameterize the design space, like you were showing with the NURBS. That's pretty great. And so yeah, as long as you can interpolate well the simulations within that design space, you're in pretty good shape. And your results with such little training data are extremely impressive. Thank you.
No, thanks.